Thank you. Good afternoon, ladies and gentlemen. We're going to present to you the Formula FSAE chassis and suspension development. Our advisor is Dr. Andres Tremonte. We have colleagues Alejandro Diaz, Osvaldo Fernandez, Ricardo Gonzalez, and Christian. Without further ado, this is our agenda for today. Some of the topics that we're going to be covering are project scope, design goals, and alternatives leading to prototype development, and finally some global aspects of our project. So Formula FSAE, as you may or may not know, is a collegiate design competition hosted by the Society of Automotive Engineers. And in essence, what we do is we build a Formula-style race car and compete against other universities. The reason we participate is to gain the hands-on experience and skills that we will later on need in our careers. And some of the FSAE design trends in terms of chassis and suspension nowadays is using a tubular frame and a space frame for chassis and double wishbone suspension. As you can see here, the vehicle is divided into systems. This allows us to work in parallel and work effectively against the clock. Our project scope encompasses the suspension and chassis. And because we are still part of the organization, we had to collaborate with the rest of the group in order to make final design decisions. So this is the typical design process that Formula FSAE teams use for developing the chassis and suspension. We first start with analyzing the tire data. So we, based on the forces on the tire will behave differently and want to be at a certain position. So from there, we develop the suspension hard points in space. Then we design the chassis around those points, and then we improve the performance based on the goals, and we test and tune. Now, what we did, because we were still in Senior 1, we were in the 2014 competition, which is in May. We tested and tuned the prototype 1, which is that year's vehicle, and then we used that as the basis for the 2015 car. So for our timeline, as you can see here, most of our efforts went into research and development because we were still developing. We were actually developing both vehicles at the same time using the data from the previous prototype. So these are our responsibilities as we distributed them. We worked in parallel, like I said, but our final design decisions were made as a group. Our basic goal was to reduce the weight of the components of the system for performance, and we want to increase the roll stiffness. This would allow for a faster transient response time in tight cornering situations, and to reduce the cost of manufacturing was also in our agenda. As you see on the left, this is the chassis of prototype 1, the 2014 competition vehicle. This is the final assembly of the chassis, suspension, and steering systems. For prototype 2, one of the unique features that we had was that we removed the rear box to allow serviceability of the drivetrain and to reduce the weight. As you see here in the iterations, some of the key differences are better triangulations, and we changed a bit on the rear to accommodate for the suspension geometries. This is our final frame. Highlighted in blue and red are, per rules, the wall thicknesses, different wall thicknesses. These are thicker members of the structure. These are for safety regulations of the competition. Here we have the final suspension geometries. These are the AMs. They were all chromoly as well as the body. And those are some of the dimensions of these parts. So this is our final CAD drawing. Like I said, okay, so the front was push rod actuated suspension, and the rear we have pull rod suspension. This differs from prototype 1 in the rear because of the removal of the box and because of packaging constraints.
So before developing any components of a vehicle, the overall design goals must be determined, some of which include the wheelbase and the track width of the car. Now the wheelbase being the distance between the front and rear wheels, and the track width being the distance between the left and right wheels. These affect how loads are transferred between the four wheels in any dynamic situations. Thus, they're important to consider in terms of performance. So using a lab simulation software developed in collaboration of FSAE teams, we observed the effects of changing wheelbase and track width. As you can see, a 60-inch wheelbase unilaterally provides faster lap times, more so when you increase the track width of the car, which is why we went with the 60-inch wheelbase. So afterwards, an analysis into the characteristics of the tires must be done. So typically, the raw tire is tested by nonprofit organizations, and then the raw data is given to FSAE teams for us to interpret. It's important to do this because the tires, all of the forces produced by the car are effectively generated by the tire. Thus, understanding the tire's characteristics allows you to optimize its performance, improve your overall performance goals of the car without losing grip, ensuring that you don't lose grip. So over here, we did a MATLAB analysis of 2 tire compounds available to us, given the fact that we were running 10-inch wheels, the Hoosier LCO and the Hoosier R25B. These tires have similar characteristics, but there are some key differences. The R25B generates its maximum turning force at smaller steer angles of the tire, which is good for drivability, and it maintains it over a broader curve. This allows the driver to easily be able to generate maximum turning force and sustain it without losing grip. But the LCO tire compound, as you see on the left, generates a maximum amount of lateral force, turning force, and is less susceptible to changes in the camber angle, which is the tilt angle of the tire. So even though this tire is less drivable, that drivability can be mitigated through driver training and driver seat time. But this performance cannot be mitigated unless you use expensive aero package. Thus, we chose the Hoosier LCO tire compound for our vehicle. And next, an analysis in the suspension geometry must be done. When you steer a car into a corner, due to the lateral accelerations, the body of the car will want to tilt outwards, and this pushes the wheels outwards towards positive camber. Using a commercial software called V-Suspension, we study the effects of this roll angle versus the camber angle of the tires. And by doing this, we're able to set the static alignment of the car, statically sitting still, so that in the middle of a turn, the tire is perfectly perpendicular to the road, and you have maximum contact with the road for maximum grip. A similar analysis is done in the rear suspension. So afterwards, drawing free body diagrams, we analyze some of the forces that the suspension A-arms will experience due to this cornering load. And using SOLIDWORKS simulations, we develop the stresses and overall factors of safety. Notice these factors of safety are generally a little bit high. High factors of safety in suspension arms is desirable in case you hit potholes or in case you have shock loading, especially in the rear where you're packaging the drivetrain, the engine, and the driveline of the vehicle. Also notice these factors of safety are relatively high, and this is because we're using off-the-shelf materials and we don't have exact control over the thicknesses of the tube members. And finally, a motion analysis of the belt crank and the shock and springs. So the installation ratio relates the vertical distance of the wheel to the vertical travel of the wheel to the linear travel of the shock and spring. And it's important to ensure that you're maximizing the use of your shocks and springs, because if not, then they're not going to perform effectively, and why bother have suspension? So as you see from this analysis, in full jounce, which is the wheel fully upwards travel, we have full use of the shock and spring. And similarly, in full rebound, which is the wheel is fully extended downwards. Now Osvaldo will present analysis in the chassis.
Thank you, Ricardo. So now we're going to go through, next couple slides, we're going to go through some of the simulations we conducted in order to replicate some impact and rollover scenarios. Here you can see we applied these forces. These forces, let me mention, these are the suggested loads by the FSAE rulebook. So we've applied these loads to the top of the main roll hoop, and we resulted in a maximum displacement of about 11.8 millimeters, which is well under the maximum allowable 25 millimeter range. Here we've also applied the similar loads to the front roll hoop with a resulting maximum displacement of about 18 millimeters. The reason we do the front roll hoop and the main roll hoop is in case of a rollover, these are 2 points of contact with the ground and the main factors of safety to the driver. And here we are simulating what a side impact would be, and resulting in a maximum displacement of about 10.5 millimeters. And we see that the maximum displacement would be in the upper side impact member. The reason for that is the upper side impact member is the most perpendicular to the applied load. As we see here, we've simulated a front impact scenario with these loads and achieved resulted in a maximum displacement of 21.8 millimeters. Something I would like to mention is that forward of the front bulkhead, there will be an impact attenuator which will mitigate some of these loads. And here we have a comparison of prototype 1 and prototype 2. As we can see, prototype 1 in 3 out of the 4 scenarios did displace less, but we just wanted to represent that both prototypes are well within the maximum allowable displacement range. And here we were going to go over some of the ergonomic verification we did on the chassis. When working with the Formula FSAE team, you have to consider all components of the vehicle. So we've included both the drivetrain, the powertrain,
the pedal assembly, we've also included some templates which must be fitted into the vehicle in order to pass technical inspection. We've included the cockpit opening template, which must dip below the upper side impact member in order to qualify for the dynamic competition. We've also included the leg intrusion plate, which must reach within a 4-inch margin of the rearmost pedal in its inactive state. If this plate comes in contact with anything in the front portion of the car, you do not qualify for the dynamic events. We've also included what the FSAE rules depict as the 95th percentile male. We've placed them in our chassis, and these lines would represent the ground in case of a rollover scenario, and the driver's helmet must be a minimum of 2 inches away from either of these lines at any point, at any time. Otherwise, you will not qualify for the dynamic portion of the competition. Here we have a quick comparison of Prototype 1 and Prototype 2. We see a significant reduction in weight, as well as a reduction in overall width and length. We also see a significant difference in torsional rigidity. Reason for this is that upon further analysis, we realized that the previous prototype was far too stiff. It would give us adverse handling characteristics during the dynamic events, and we've reduced this number to a range which is a lot more seen amongst other teams that run our similar setups. And here we have the chassis mounts, which will fix the suspension to the chassis itself. You can see a representation of how it will be applied in the rear suspension. We see that most of the stresses are located on this back plate. We will have a nut on either side here affixing this chassis mount to bolts which will protrude out of the chassis. And with this design, we achieve a factor of safety of 3.7. Something that originally we did not consider for our project, but we later took it upon ourselves to assist the team in this matter, was the hub situation. There was a improper use of a thrust bearing on the hub, which would cause the wheel to seize up when the lock nut was tightened all the way down onto the axle. Typically, or ideally rather, you would want a tapered roller bearing for this type of scenario, but that would require too much redesign manufacturing, and we simply don't have the time or money to produce something like that. So we proposed this design, which we then followed through. We have a quick video showing that it's free spinning. We have a prototype here as well. Something else that we decided to include in our design is the steering rack location. So strategic placement of the steering rack fore, aft, as well as vertically within the car will mitigate both bump steer as well as prevent over-centering while you're driving. So over-centering would be if you were to turn the wheel full lock in one direction, the arms would fall into a situation where it would prevent you from wanting to turn back. So it would basically lock you in that state, and you wouldn't be able to finish the turn. You'd either lose grip, and you know what happens after that. Now Alejandro will walk us through a prototype development phase.
Thank you. So for both prototype 1 and 2, we use similar manufacturing techniques, which include for the chassis, we outsourced our tube members, our chassis members, which were pre-cut and notched, as we see here. And then in-house, we designed and manufactured a jig, which is important when assembling a spaced frame, which you use a common reference point, and you always use the levels and the earth as a reference point, making sure all members are properly aligned. For the suspension, we also will use the same techniques as prototype 1, which is applying all arms to a jig, making sure they don't warp during welding. This next slide is a quick little time lapse we put together the past few days when assembling the chassis. Please note this was all done in-house in our student machine shop. Also note the jig on the bottom. If you can notice it, is there. We have that in the student machine shop. We didn't bring it up. The arms were, and the rest of the suspension, some of it will be outsourced to water jetting to hit better tolerances and things we cannot do without access to CNCs that we don't have in our student machine shop. So how we've approached prototype 1 and 2 for choosing who to outsource and what to do with our chassis. The first row we see is a price of about $850 if we would do the whole thing ourselves, which we did about in 2012. We did it ourselves, and it took about 2.5 months to just finish the chassis. And this includes cutting, notching, bending, jigging, and welding all in-house. The next choice would be using a company called CRD. And this company pre-cuts and pre-notches, as I showed you, using a laser notcher, which is always perpendicular to the pipe, which is a little bit cleaner than actually mill notching, and a little bit easier for our assembly. And then the only thing we would have to do in-house is the jigging and the bending and the welding. And our last choice would be a company called Cartesian, which would cost about $2,600, and they would do everything for us. All we would have to do is, when our pipe members come in, jig it all together and weld it. So we ended up going with the second choice, which is about $1,200. Here's a cost breakdown of our full system, including jig, suspension, and chassis. Please note that Prototype 2 is a little cheaper than Prototype 1 just because we decided to rework and reuse and recycle some of the usable suspension components from Prototype 1. So some global ties. Being a Formula SAE organization, we represent an international organization. We go to an international competition, and we do follow a rule book that is international. Also, we have access of engaging other Formula SAE teams, which we've done for this semester. We've engaged with Saginaw Valley University, and they helped us guide us a little bit through picking a few components. We've also had a technical group contact us in Colombia. And also this past semester, we've had the pleasure of going to 2 local high schools, presenting our senior project and educating the STEM education using the Engineer on Wheels program. So some economic and environmental considerations. So as you see in the bottom right, this is a list of how they grade us or how they give us points in a Formula SAE competition. Please note that one of them is in static competition is the cost analysis. So in developing a vehicle for Formula SAE, you have to consider the mass production in mind. You have to turn in a cost report. So with this in mind, every time we've designed, and I always preach this to the rest of the team, anytime you're designing, I'll always think of mass production in mind. You have to produce things with cost per value in mind. Also, please notice that in that dynamic portions, there's an efficiency portion to this, which also entices us to design a lighter car, which in turn, a lighter car will use less fuel consumption, will in turn give a smaller carbon footprint. We've also decided, since we're reworking, we recycled a lot of the components, which is good for the environment. Also, most of the scrap material in our machine shop is recycled. So for lifelong learning, having the pleasure of being part of an SAE organization, it's incredible for us to apply things that we learn in classrooms into real-world scenarios. All 4 of us are very passionate about the automotive industry, so learning things, applying dynamics into automotive scenarios really opens your eyes. Just a small example, we learned how to team building, as we mentioned before. We designed chassis and suspension, but with all 6 components of the vehicle together, so we have to not only work with each other, but work with the rest of the team. Also, engineering foundations or fundamentals. When developing chassis and suspension, you understand 2 important components of vehicle engineering, which is vehicle dynamics and vehicle integration. Whether you work in that field or not in the automotive industry, those are 2 topics that will come up frequently, so it's good to have a good base as we learned in this project. And this, I'd like to point out, in this magazine, we came out in the November magazine of SAE, and here's just a quick glimpse of us during competition, actually with the industry advisors, kind of going over all our design decisions in SAE competition, which is great. So in conclusion, we reduced the cost by 18% from Prototype 1 to 2. We had a weight reduction of 26%, which was very important for us to achieve. Length reduction of 10%, width reduction of 23%, and roll stiffness increase of 13%. So here's some of the standards we use in this project. Just for example, just the metals we use are generic 4130 chromoly, the 6061 aluminum fasteners, which is very important. Grade 5 and grade 8, which is important during technical inspection. They do check all that. And of course, following the FSAE 2015 rulebook, very important. I would like to take this opportunity to thank all our sponsors. Without these people you see up here, we wouldn't be able to have a Formula SAE program in this university, and on top of that, have projects like this. Thank you.
Comments, questions?
Yeah, I got when I start, I got a question. Could you go back to the slide where you had the side view of the old Type 1 and Type 2? Drawing. No, go back. The other way. No, okay.
No, go for that.
The beginning one, right?
Right there.
Little
Okay, let's just use that right there. Okay, I see you're sitting you're underneath the rear hoop there, and your engine's right behind you. Where's your rear end could be sticking out? Sticking out of the side of the chassis, or?
No, would be, you mean the drivetrain, so the differential,
Right,
floating?
floating.
Yes.
Okay. The reason I asked that, before SAE, was one of the founding fathers. And I'm looking at that and I'm thinking you're gonna have a lot of packaging issues with this newer frame here. And I know the rules have changed a lot. I haven't read the latest one, so I'm not sure what it is. What have you encountered? What kind of issues putting this, I mean, you guys haven't put the whole thing together yet? Not yet?
Not the vehicle.
What issues do you anticipate happening when you start putting it together with this frame versus the other frame?
So, we'll go around, I mean, I'm sure we all
Sure.
have pretty valid points. For starters, engine packaging was probably the most difficult, obviously, that's where the engine goes.
Right, yeah.
So, we had to figure out.
That's what I was looking for,
Right.
yeah.
So
Okay.
we wanted to figure out basically where all the hoses would go, the catch cans, things of that nature. And what we've come up with is, which is similar to what we've done previous year as well, is if we see the angle of the driver, seated position, provide space for the fuel tank, catch cans, other components that would otherwise go in that rear box. So we would have a firewall integrated into the seat.
Yeah, okay.
That's the intent.
Well, that's the rule, you gotta completely separate all fluids
Yeah.
from the driver.
Correct.
Okay. Now, as far as a float like that, there's nothing in the rules now to say it's gotta be protected somehow?
No, not from a rear collision.
Not for real?
So yeah, in motorsports, basically, you guys try to make a competitive car. You really try to work exactly where the rules tell you what not to do, and you work right on that threshold.
Right,
So basically, they haven't started implementing, as in Formula One, they do have a rear crash box. In Formula SE, they do not have a rear crash box. So you see, we came up with that idea looking at, we had the pleasure of running competition twice in Michigan, and we came up with most of these ideas just walking around the pits and seeing what other teams are doing to be innovative and to get lighter weight, because prototype 1 was way too heavy, as we saw, and we studied and analyzed all our critiques from the design judges. They just said the car was way too robust. As we saw in our torsional rigidity, it was just way too stiff, way too robust.
Yeah.
So we learned that from prototype 2,
So
which is
probably
why we lightened it up.
The only probably safety aspect of that would be the chain guard, which is still being implemented.
okay.
But that's more for, to protect a personnel from walking behind the car,
Right.
coming in contact, snagging your clothes rather than a rear end collision.
Right. Now, also, while you're driving down the track, if that chain breaks,
Yeah, exactly.
you gotta
Yeah.
have that card to
Yeah, the
catch
chain guard will
chain.
protect from all the chain links exploding all over the place.
Okay. How comfortable do you think this seat will be?
Sorry?
How comfortable do you think this seat will be? Because I'm looking at that really low angle, your neck's like this, and you got a big helmet on you. You know, you gotta take that into account too.
Yeah. So when we do like the ergonomics integration portion of it, we really just throw 95th percentile in somewhat of a comfortable position. But on top of that, if you open up our paper, we did an ergonomic rig, which is out of wood first, before any of this was ever present, and we kind of sat a few members of ours from the shortest to tallest and kind of took a few measurements on that jig
Okay.
of wood, and then we kind of just translated it into what you see on CAD.
Also to note that the driver's seat position and the pedals are adjustable, so we
Right.
can adjust it in order to fit the driver. This 95th percentile is a guy who's like 6 foot tall, which is none of us. So when we actually have the pedals and we have the seating, we can recline the driver in a more comfortable position for him. This is just to make sure that the template they use in competition actually fits within the rules.
Right. Okay. That's my last question, sorry guys.
Any other questions?
I have a question. So what type of analysis did you do that was different from the last one? So I know you guys made a different design, but what was different in the analysis from one year to the next?
Well, last year there wasn't exactly a comprehensive analysis of the tire data, which is really important because the basis of the suspension is to maximize the tires. So by analyzing the tire, we can see exactly what the tire can do, and we can reduce optimize the suspension and therefore reduce the chassis weight, because we realized we were able to work all these different systems in parallel and put them together in order to improve the overall performance of the vehicle as a whole.
For instance, for prototype 1, our suspension, adjustability was like from -8 degrees of camber to +8 degrees of camber. And so for those of you that are not educated, that is way too much. Our tire, after 1 degree of camber, is really useless. So in turn, it made our suspension mounts roll outward and cantilevered, which we got points taken off during the design competition. So we came back and we assembled during the summer, and we kind of discussed what was good about the car, what was bad about the car, and then those were all the engineering decisions we made towards prototype 2.
So I would just say all of those are good, right? But just for you guys, this is kind of a continuation thing. It might be worthwhile to try something new in terms of analysis methods. I know you said you're just adding more, right? But maybe try something new each year too, just so that way you're not doing the same thing over and over, just making 5% increment improvement, right? Maybe you're try something and get really terrible, right? But it helps with, again, you learn more by really going outside of kind of the typical things that you do each
Absolutely.
year. Yeah.
Thank you for that. We'll keep that in consideration for the future team.
Yeah, just,
Yeah,
I mean, you guys are
Yeah,
not
we
here, so it
had
doesn't
access
matter,
to
but yeah.
a few softwares, but just, with timing and learning the software and actually using it efficiently, we actually kind of we had like a loaded software for suspension that we kind of started learning how to use. We got it for free being Formula SAE, and then we just kind of halfway through the semester we were putting way too much time in, and that's when you kind of all have to step in and we're like, just keep on going. No, we're never going to finish.
Yeah, it's really hard to balance that.
Yeah.
The other question I have is kind of related to the simulations again. I know you did the simulations and you got numbers out that fit well, but how confident are you in those, and did you do anything to kind of back up the fact? I mean, a real person is going to be in that car, right? So we can't just say, okay, max displacement was 18, right?
So we used these simulations more as a comparison to compare the two prototypes, because this is only required for frames that fall under the alternate frame rules, which would be using alternate materials or deviating from rules such as maybe this bar is required to be one piece as per the rules. Let's say the team doesn't want to do one piece, they want to do multiple pieces. They would have to provide these simulations to the Formula SAE competition in order for them to even approve the construction of that frame. So in reality, we use it more as a comparison between the two prototypes.
But I guess my question is confidence in that.
Yeah, in addition to this, in the rules, they specify how you're supposed to fix each member of the frame, how you're supposed to apply the loading, and how you get the results. They walk you through it step by step to make sure.
I mean, yes, I agree with you, right? So you have a starting point, but again, what you put on the front end is important, and a lot of other things in terms of, again,
I guess,
but it's really your mesh density and all sorts of stuff can make a big difference. right?
Testing this, you would need number one.
I agree with you, right? You can't go put 9,000
I don't want
kilonewtons or whatever it is.
Personally, I
yeah,
wouldn't
right.
want to give a confidence value when I physically haven't tested the prototype experimentally. You would have to actually destroy this car.
I agree with you, right? But then you're going to put somebody in that car, and you're going to ask them to trust you, right? So, and then if you give that answer to me, if I'm riding in that car, that's a totally different story, right? So that's what I'm saying.
But per the FSE rules, they take a lot of precautions. Like
I
know,
so
but this is the same problem that you raised to a previous team. Yes, you may have to use their software and you qualify that, fine, no problem, but independent from whatever else's program you're using, you really need to verify your calculations. That's not just true for this design, it's true for any design you do. Because if you trust someone else, FAE may have beautiful codes, whatever, but you may enter the wrong units.
Right.
And NASA had to scratch its entire mission because of inch-millimeter problems. So there's no excuse for that. In general, all teams need to verify their calculations independently. You cannot trust someone's commercial software. That's a general rule. He's making the point, and he's totally right.
And it's called the Gigo effect. The Gigo
Garbage in,
effect.
garbage
Garbage in,
out.
garbage in.
Yes, please.
Okay, I assume these are all just tack welds? I'm not looking at a finished product here, correct?
No, you're not. It would require much more time.
Okay, so what is the protocol there on the welds?
Well, we welded it to the point where it wouldn't fall apart moving it, so we can bring it to the presentation. But it is far from complete.
So all of those will be autogenous, full, complete welds?
Yes, correct.
Okay. The only other question I have is that in the report you state that during the Formula SAE competition, you realized that there were problems in your hubs, your bearings, your spindle design selection, and proper integration. How in the new design have you made changes to these?
So typically, we took apart the hub and the upright in order to figure out where exactly the design was going. And that's why we have the slide where we show you the thrust bearing and we show you where it was going on. So then we did our research, we pulled up some Timken engineering manuals, and we looked into exactly which bearings are appropriate for the applications, and then we picked the bearing accordingly to that. And then afterwards, we made sure that the press fits, thanks to the help of Mrs. Acrylic, we made sure that the fitment of the bearings and pressing into the hubs and pressing into the shafts were good enough so that they would free spin without causing excessive binding or excessive stresses to the bearing. And that's how we modified from last year to this year.
But have you done any experimental testing on your new design
Not yet.
to confirm? So no
Just a
test-
quick suggestion,
no
you have
testing
the old
today?
one, right? You're not gonna use that one anymore? Do some stuff on that one, you know what that is, right? Throw a whole bunch of weight on that and compare your simulations on that one, and then you feel more confident with this one, right? That's just.
So I mean, I didn't want to call experimental testing bolting it on and spinning it at the shop.
Yeah, I understand.
But the old ones were so bad you couldn't do that. Because it was improper translation of forces through the bearing. You want to translate the bearing from the inner race to the ball bearing to the outer race. We were just translating it through everything. And why you see the scrap, the material on there. So just because timing and Formula SE trying to make it a
So when's
competition and travel.
all of your portion going to be completed? So,
Due to logistics with water jetting, we have a few of our components for the suspension, that's why it's not assembled. We're sent to water jetting. When we get those parts back, it should take about another 2 weeks to assemble, jig, and just weld up everything.
Winter break.
Okay. Do you have, yeah, please,
Yeah.
we're running short.
Related to the welding, and I'll make it very quick.
Okay.
You've done SolidWorks, you've done some analysis, so you know what's going on with the stress and strain and the frame elements and all of that. So if that is all good from your analysis, the joints is gonna be where the weak link is gonna be. I heard the question about welding that you will do later on to ensure that there's integrity in the welding as well as in the frame. I didn't see where you spoke about any kind of NDT or other destructive testing to verify that integrity. Could you speak about that real quick?
Right, so the Formula SE competition, the competition requires a team member to weld the frame. You can't outsource that. And with that being said, the team must bring 2 test welds to competition each year, one at a 90 and one at about a 30-degree angle, inside angle, and they test it. And if those welds do break, then you'll be able to not qualify for dynamic events. And of course, if you pass, they continue and they do sonogram testing on your pipes, on your welds, and continue.
they do sonogram testing on every structure as part of the...
Yeah, right. They've seen so many that they can, by eye, basically kind of say, well, this is a little weird.
The main ones that
Check
test are
this
the
one out.
095 wall thicknesses of these main row hoops, which is what will prevent you from binding under or buckling under a roller.
Okay, thank you.
That's what I wanted to highlight, that safety for them is so important. And when they allow us to use some software, it's already FSAE certified for that. So we have to have some level of confidence. If not, we start just saying, putting question marks everywhere, so we won't finish, never. So it would be a never-ending process. So that's part of the job, the balance between confidence and safety.
And SolidWorks is one of their sponsors too, so I'm sure
Exactly.
it's part of the business.
The rear hoop, the front hoop, and the very front hoop, all that's one big piece.
Yes, as per the rules, that needs to be one piece of 095 wall thickness.
They changed that rule when I was trying to put our frame together. But we had 2 pieces.
Okay, thank you very much.